This is my tablet, a Cube by 7 Stylus. This tablet is pretty awesome. I made a couple of videos about it. The only downside that I still have left after replacing the Wi-Fi and the Bluetooth and doing some other mods to it, like the SSD, which you can all find in previous videos, there is this slight niggle with the power inlet port, which is a relatively non-standard 12-volt DC power input. Tablets like this have great battery life, but sometimes you want more. Power banks exist, but almost all power banks designed for tablets have a 5-volt output, just like for phones. Because most tablets are not Windows 10 machines, right? Hello. They are like Android machines, much lower power, much lower processing power, but also much lower like electrical power, which means 5 volts, 2 amps, just a basic BC 1.2 standard is enough. Now, not for this one. When it's charging, it can draw up to about 20-25 watts if it's also on. They had to use 12 volts, pretty much. And that has the side effect that if you go and look for power banks on the internet, 12-volt power banks are mostly absent. The ones you can find are like they have nice brushed aluminum surfaces and they are very sleek looking and they are $200. Or they're made for some other purpose and have very inconvenient sizes, are very heavy. Some are heavier than the entire tablet. It's just not a very good look. So what I decided to do is design my own power bank. Wait a second, what's going on here? This is my own design power bank. It is a Focus. Thank you very much. It's got an on-off switch and a nice blue LED. It's got a charging in port. So this is a USB, actually a USB 3 charging standard in a USB 2 micro format port. So it draws up to 3 amps at 5 volts to charge up the power bank. And it's got this MiniFit Junior output. This outputs the actual 12 volts. Then it's also got 2 5-volt 2 amp USB outputs just for like charging your phone. Internally, there is 4 high capacity cells. These are 3350 milliamp hour cells, so about 12-ish watt hours a piece, slightly more than 12 watt hours. Low battery shutoff circuits, just an NMOSFET and a voltage supervisor. Obviously the on switch, some LEDs. The charging circuit, it's kind of tucked away here. And then the big converter here, this is a DC-DC boost converter, giant choke. This produces the 12 volts, and then there is a 5-volt circuit here as well. That's basically it. It's not very complicated. It doesn't have auto shutoff. It has that actually for a reason, because a lot of projects that I want to power with this that run on 5 volts, they just use too little current, and most power banks with auto shutoff function will shut off at like less than 50 milliamps current draw. That is way too high of a threshold for my projects, which often only use 1 or 5 milliamps. And this thing here is a temperature sensor for when it's charging and it senses over temperature, then it will stop charging. It will not stop the PCB from discharging from the cells. The whole thing is built to be reasonably power efficient, has a fairly low, like if you accidentally leave it on overnight, it won't drain at all, pretty much. It will drain like maybe 5 or 10%. This project was in collaboration with somebody else. I actually did all the engineering on it, but the other guy really wanted one and kind of had the idea. The enclosure here is from AliExpress. I bought 10 of them. They're about $5 each. And then here on the end, this is just a 3D printed part, because as you might be able to see, if I hover this above the power bank. The PCB and 4 cells will not actually fit. It's just slightly too large for the enclosure, so I had to extend it slightly, and honestly, it looks pretty good. And like a lot of these enclosures, they have like these little notches where you can slide in your PCB. And this one, the drawings were on AliExpress, so I could design against this, and I designed it to fit into the lowest slot, and then the USB port just about fits. Having exposed electronics is probably not the best idea, so why is there no faceplate on this? And the answer is there is, but it is misshapen. This is the revision 0 PCB, so I just designed it and bought it. And as you might be able to see, I have to do this one-handed. Yeah, the faceplate kind of sticks out about 2 millimeters. And there are some other slight issues. I actually had to file off some corners, and well, it's just not great. So I redesigned it, and I thought this video might be cool to show you the process. So to show you how stuff is designed and how I put it all together and how I think about this design process. So as you can see, I bought PCBs from Crow. It's a weird name, I know. It's one of these cheap Chinese PCB manufacturers where you can buy 10 PCBs for $10 essentially. So let's just look at the PCB itself. By the way, this design is open source. Just like my nanohabs, you can go to muxtronics.nl, click on open source Powerbank, and then you can see the entire design. You can see some more specifications, and you can download the schematics to see for yourself how it works. But anyway, as you can see, this is not the same as the power bank that I showed you. In fact, if we just look at the other faceplate, this one's obviously smaller, so probably fits better. Oh wait, there we go. That's the correct orientation. You can see how much I was off on this one. What I do here is I don't order many separate PCBs. I wanted to have the faceplate, I wanted to have just the main electronics, but I also wanted to have the temperature sensor, and in this design I added 2 spacer strips as well. And the real way to do this is not to order this and this and that and that and that PCB separately, because this will cost you like, it's larger than 50 by 50 millimeters, so this is like $13, this will be $13, this would be $10, and these would be $10. So the whole design together would be much more expensive if I would order all these boards separately. Instead of what I did here, which is using break-off tabs, I added a little bit of PCB material in between these PCBs, and then I used very small drills to, these drills go all the way through the PCB and kind of weaken the material here. And I will show you in a second that this means that this whole PCB snaps off very easily and very cleanly without damaging tracks or anything. And all you need to do is snip off, use some side cutter snips to snip off this little tab, as you can see I've done here. And you have 2 separate PCBs in one design for a lower total cost. So here you go, let me show you. These snap off like that. These mouse bites, as they're called, the places where you break it off. They do leave these little pillars going out, little nubs. You don't want that, because this side of the PCB faces outwards, and actually it sits flush against the faceplate like that. So you want this edge to remain clean and not have little things protruding. So I actually inset the mouse bites slightly so it wouldn't have any material sticking out. Now, actually, does have like a fraction of a millimeter sticking out, but I think that's okay. It's a lot better than other mouse bites. And well, Same goes for these little PCBs and the little temperature sensor. The issue I was having with this PCB is, as you can see, when you plug something in, you actually put some force against the PCB and it has the tendency to shift about. And what I thought would happen is, well, the batteries are behind it, so the PCB will just be supported by these batteries. In reality, it's just a very mushy feeling of putting something in. It doesn't feel very reassuring. And also, like the batteries, they have been packed. This PCB, I mean, the edges aren't that sharp. It's probably fine, but there is an edge of the PCB rubbing against a wire. In the long term, it's probably not good. So I needed some other kind of retention. Also, there is metal here and metal here, and there is a connection strip here and a connection strip here. What happens if the Kapton tape around here on both sides gets worn away? Then these batteries can short. So what I decided to do is to add in these strips on the side, and these slot into the bottom here, and I actually plan to glue them in. And these go all the way to the back, sit against 3D printed part, and they serve two functions. Number one is they hold this PCB in place, so the PCB will be essentially wedged between the strips and the faceplate. The other function is that they are actually slightly wider than this channel, as you can see, so they will keep the battery centered and not touching the metal at any time, even when the Kapton tape wears out. There's basically no danger of shorting the batteries. So now all that remains is to, I checked here whether the faceplate is actually good, and it is. It is actually very well matched. Really like how that came out. You can see it's kind of, I like the red and black theme. Kind of looks like a battery, right? It's got a red top. I don't know. So everything fits. I'm going to assemble a board, and we're going to test it out with the cube. All right, just to show you through essentially the entire process, I just applied solder paste and placed all the SMD components. So that's the components that don't have legs that go through holes. And I use my hot air gun, and no, that's not a euphemism. That is a hot air gun, blows hot air, to melt the solder and electrically connect all the components to the PCB. Now the next step is to mount all the components that are through hole. Right, so now everything is together, and I decided not to show you the soldering. You know how to solder, and if you don't, then plenty of videos on YouTube. The next thing is testing, and the fun thing about this that I found out quite soon in its development is I have very little input capacitance. This is essentially the only input capacitor that I use. So the current drawn by this giant DC to DC converter can be quite high. The current limit, which is set by the this resistor here, is actually something like 15 amps. So it will draw short pulses of, I think it's something like 9 amps on startup. And my power supply cannot deliver 9 amps. So I actually have to put a battery in series just to deliver the startup current to test it. Unfortunately, that has the side effect of being a little bit scary, because that battery, specifically this one, it can fry this pretty easily. So let's hope that I assembled everything correctly. Right, so it's all hooked up. The battery, it's positive here, negative here, hooked up to the battery terminals, and then the battery is constantly being recharged essentially by the power supply. So what we want to see when we flip the switch to there, we want to see everything turn on. We want to see 12 volts on this output, and we want to see exactly 5 volts on that output. So let's turn it on. It is on. It is not showing a low battery here, so that's good. and the power supply is not seeing we're drawing a couple of amps extra, so it's definitely not heating up right now. This output should be 12.15, that's what 12.13. And then here, this should be 5 volts, and it is indeed 5 volts. Now we have to look at the charging circuit. For charging, what I did is I built this cable. This is a high current BC 1.2 cable. And what this is, it's just a regular micro USB type A. And here under the heat shrink, there's a short between the D plus and D minus lines. And the actual power lines just go through these thick wires that will be put into my power supply. So what I want to see when I plug it into the charging port is that it starts charging at a considerable rate. Maybe it doesn't actually sustain 3 amps, but I would like to see between 1 and 2 amps, because I think this cable will be able to support it. Now, one thing that may happen is that the charging circuit doesn't like it that the temperature sensor is not connected. And in that case, we will see the green charging LED blink. Okay, so it's plugged in, it's at 5 volts, current limit all the way to the right, and see, it's blinking. So we're gonna have to assemble the temperature sensor, just hang it off a couple of wires. And there is now a temperature sensor here. Well, it is charging. Solid green LED, but it's only charging at about 1 amp. And here we go. This is the finished product. There are actually no cells inside. It's very light. But this is just to show. This camera has a touchscreen, which allows me to say where it should focus. Should use that more. I put in the strip, the board on top of that, and then the faceplate. Well, the faceplate just looks great, and the cutouts are fine. But yeah, that fits well. That fits well. This should also fit because that already fit last time. No, it actually does fit. A little bit more snugly than last time, but still fits well. And the micro USB charging input. Let's see. Yep, also fits. All I need to do is weld together the batteries, pack them into Kapton tape, solder it on, and then I have a full power bank unit of my own design. Alright, my favorite part has just arrived, the battery cells, and we're going to weld them together on my trusty Sunco 788H, which I modded to be able to work on normal power outlets. By the way, many people have contacted me since to say that these are actually designed to be used on industrial outlets. They're supposed to work well on 63 amp breakers. That is a pretty ridiculous current rating, and totally not necessary, because I can get just fine performance. I can get full like 80 or 100 amp welds with the microwave transformer that I use. So I don't know why that is the case. It's probably just an old design. Anyway, another thing we're going to use is this, which I bought off of eBay. This is a battery tab, which is a very long one. Battery tabs are surprisingly expensive if you want to buy them. Like ready-made tabs for a certain pack length, especially the high current tabs, they can be $2 each. Why would just a strip of metal be that expensive? But I found this, which I think is 5 meters for a couple of dollars. It was really cheap compared to others. So I'll link that in the description below. And this is high current tab. So I'm going to be welding that at 60 amps and 2 pulse. By the way, I almost forgot to mention, I'm going to put 4 cells in parallel. If you're going to build a pack and the pack is made of for instance, salvaged cells, which I do use from time to time, salvaged cells are going to have different capacities, but you can put them in parallel. That is no problem. They will just charge to the same voltage, and some of them will output more current than others. That's all fine. However, if you weld them together when they are at different voltages, quite significant current can run from the fullest cell to the emptiest. So make sure they're around about the same voltage when you weld them together. It's not super critical. They don't have to be within a couple millivolts of each other. They can be 0.1, 0.2 volts off. That's fine. Just not like one is empty and one is completely full. However, I will be using genuine Panasonics from a trusted importer. These come in the box at the same state of charge, so I can just pretty much blindly weld them together. Readjusted the camera for you. For these high current applications, I do like to at least put in 6 little contact points. So for this was just the first battery. So for the next few batteries, I will be using this little contraption. I put in batteries side to side and then weld them together in here. That way I know for sure the spacing is correct. All right, so here's the second battery. We just tack that down with, again, 1, 2, well, I suppose we'll do 3 like that. Fourth battery. There we go. And then the final battery. And there we go. Now we flip it around and do the same thing on the other side. So there we go. Now you may have noticed I use quite a lot of welds for this. Some people, they go ham. They put in 20 welds. Usually in the factory, like if you see very large battery packs for power tools, for instance my Milwaukee drill, they only have like 4 or maybe 6 weld connections, and you don't really need more. The connection is going to be fine, but obviously I'm working on kind of a low-end device. I don't know for sure that all my welds are going to be perfect. So I choose to use a couple more welds than absolutely necessary. Now on the board, the negative connection is on the outside and the positive is on the inside. So I want to orient my battery pack like this, with the negative side up. And so a slightly longer wire is going to have to go on here, and this side will only need like a very short wire. Soldering onto the battery cells themselves is quite hard to do, but these tabs are just very nice to work with. And here is our wire. We just solder that onto the tab. And now we have a good high current connection to the wire. The wire can be soldered to the board again. All right, it's time for some Kapton tape. And then there we go, pretty much. I do still need to put the temperature sensor in here somewhere. I usually do that by cutting a little hole in the Kapton like that. Making a little flap. And then simply tucking it in there to make sure it actually touches the cells, like that. And there you go, that's the finished unit. So I'll just slide it into the enclosure and we'll be done. I am fast running out of daylight. There we go. And for the faceplate, I'll also need a, well, maybe I can do this on camera because, well, I am known for being very optimistic. And well, there we go. It's fully assembled. The only thing missing here is the a little 3D printed part to make turning it off and on easier. But we'll get into that later. First, let's connect it up to the Q/7 and see if it works. And poof! Suddenly it's nighttime. To connect to the Q/7, I made this wire, and this is just a Molex Minifit Junior, so that's this connection. Focus, thank you. The connection here is a Molex Minifit Junior. It's actually the positive is on the bottom, which is technically the wrong way around, but that's all right. And the Q/7 connector is a 3.5 millimeter outer and 1.3 millimeters inner barrel jack. I bought those components and I put a bit of standard coaxial power wire in between, and obviously heat shrinked it well, crimped the connectors, just to make like a nice cable that will last me a lot longer than the cable on the default power adapter, which has actually been fixed twice already. So here we go. We have the trusty Q/7. Now power bank, it's on. Alright, so here we have the Q/7 turned on, currently running on battery. And when I plug in the power bank, you'll see it now says fully charged, and it is on the power bank. So basically it works. It will just charge the battery as you expect. The power bank has like a 48 watt hour total capacity, 49-ish. Because of converter efficiency, it's slightly less what comes out, but it's still way more than the 33 watt hours in the Q/7. So it will fully charge your Q/7 while working on it before running out. And that's exactly what I wanted. This is pretty much the perfect power bank for the Q/7, and of course no wonder, because I designed it specifically against this. It will also work on the Microsoft Surface Pro 4. Now unfortunately I see that the video is getting really long, so probably lost most of you, and I will cut it short here. If you're interested, if people have like a good reaction to this video, I'll do a follow-up. I will do load testing with my load tester. Obviously you want to see how well it copes. Try to do some efficiency testing, look at actual runtime numbers. I have not done that yet with this revision because it's slightly different from the previous one, which by the way I only drained 2 times so far, so I just don't have good data on this yet. I'll be making 10 of these. 8 of them are already sold pretty much to other people, and 2 of them I might put them on my Tindy, but I'm not quite sure. You're probably wondering, hey, he's making a big video about something new he designed and built. Is this just to show you something he wants to sell? Not really. As you see, it is a pretty labor-intensive device to put together. The welding of the tabs, putting it all in Kapton, soldering stuff, The board itself is mixed through hole SMD, which is like a two-part process, which I cannot do on my pick and place. I have to print parts, I have to assemble everything together, and it's just a lot of work. I've calculated that it takes me about an hour if I would do one-offs, like if I would sell them on my Tindy and once in a while sell one. An hour of my time is supposed to be about 65 euros, so that means my profit would have to be like that, which is why if you look on the page on maxtronics.nl, the Powerbank page says that if you want one, it's going to cost you $100, like 100 euros. And that's not because they cost 100 euros, they cost about 35 euros to make. It just takes me so much time, and I don't feel like making this in bulk. Maybe if the response is really good, I can make or have some company make 50 or 100 for me, but I don't think that's going to happen. Power banks are so commodity, nobody is willing to pay that much for such a small power bank, quote unquote. So don't expect to be able to buy one. Maybe one or two will be on my Tindy page, but it will be a very limited release, just to sell off the boards I made. Anyway, I hope you liked this, and if you would like to see a follow-up, please comment on the video.